In this session, we will discuss an example to implement Huffman tree and codes. Already, we have discussed what is Huffman tree and Huffman codes. And also we discussed about Huffman algorithm. Now, with the help of Huffman algorithm, we are going to solve a problem step by step. Example, consider a 5-symbol alphabet A, B, C, D and underscore with the following occurrence of frequencies in a text made up of these symbols. For symbol A, frequency is 0.35, B 0.1, C zero point 0.2 and D 0.2 and underscore it is 0.15. So what is Huffman algorithm? First step, we have to initialize n one-note trees and label the symbols of the alphabet given. Then we have to record the frequency of each symbol in its tree's root. Then arrange the notes with frequencies or weights in ascending order. Step 2, repeat the following operation until a single tree is obtained. That is, find two subtrees with the smallest weight, make them as a left and right subtree of a new tree, record the sum in the root. These steps you have to repeat until you will get a single tree. And the tree constructed by the above algorithm is called Huffman tree, and the code created with this manner in Huffman tree, that is called Huffman code. Okay, so these steps we need to follow to solve this problem. So first step, initialize n one-note trees. After initializing, arrange the n one-note trees in ascending order. Okay, so first, these symbols along with its frequency, we have to create it like a n one-note tree. Okay, so here node A, it is 0.35. So this is one node tree. Similarly, B, if you are considering it is 0.1 and C, it is 0.2. Similarly, D also 0.2 and underscore, it is 0.15. So we have created n one-node trees. And these n one-node trees, we have to arrange them in ascending order. Okay, every step we have to arrange them in ascending order. So here, if you want to arrange in ascending order, 0.1b comes first and then it is 0.15 underscore and then it is 0.2c and then it is 0.2d and then it is 0.35a. Okay, now this is the n one-node tree we have created and we have arranged them in ascending order. Okay, next step 2, find two trees with the smallest weight and make them as a left and right subtree of the new tree. Record the sum of their weights in the root of the new tree. Repeat these steps until you will get a single tree. Okay, so now first two trees with the smallest weight you need to add. So if you are adding 0.1 and 0.15, you will get 0.25 as the sum. This sum you have to record it at the root of the new tree, and B will be the left subtree, underscore will be the right subtree. And also every step you need to arrange this NO tree in ascending order according to their weights. Okay, so if you are adding these two, in the sense you will get 0.25, right? 0.25, you have to record this sum at the root, and the left subtree will be B with 0.1, this one, and the right subtree will be underscore with 0.15, right? So this is 0.25 and we have to arrange it in ascending order. Okay, so 0.2c and 0.2d comes first. So if you are comfortable, you do the step separately and then arrange in ascending order. So here I am combining, while adding itself I am arranging in ascending order. Okay, so 0.2c, it is 0.2d, you will get it, right? And then 0.25 with b and underscore, then 0.35 with a. So this is the new step we got. These two trees we have combined. Next also same procedure, step 2 only. Find two trees with the smallest weight, make them as a left and right subtree, record the sum in the root. Okay, 0.2 plus 0.2 you will get it as 0.4. So it is 0.4, you will record it at the root, and then the left subtree will be C with 0.2 and right subtree will be D with 0.2. Okay, so this is the new tree we got after adding these two, and also we have to arrange in ascending order. Accordingly I have written, so it is 0.4, so 0.25 is least, so here comes 0.25 with a B and underscore, B with 0.1, and underscore with 0.15, right? And then 0.35a. So now this step we have arranged in ascending order. Okay. Next step also, find two trees with the smallest weight. So now these two will be the smallest weight. Add these two trees. So now if you are adding in the sense, you will get 0.25 plus 0.35, you will get it as 0.6. So it is 0.6 will be at the root, and the left subtree will be this one, that is 0.25, with B it is 0.1, and underscore it is 0.15, and then this will be at the right subtree, that is 0.35a. Now its sum is zero point 0.6 and this one is 0.4. Okay, so here I'm arranging in ascending order as it is, C with 0.2 and D with 0.2. So now there is only two trees. Okay, now add these two. So if you are adding these two trees in the sense, zero point 0.4 plus zero point 0.6, you will get it as 1.0. That will be placed at the root, and the left subtree will be this 0.4, that is 0.4, with the C as its left subtree with 0.2, and D as its right subtree with 0.2. So now its left subtree is over, right subtree is this one, that is 0.6, and then 0.25, with its left as B with 0.1 and right as underscore with 0.15. Okay, and then its right subtree as A with 0.35. So now if you are considering, we got a single tree. These steps we have to repeat until we will get a single tree. This single tree is nothing but Huffman tree. The tree created by implementing the Huffman algorithm. That is, find two trees with the smallest weight in every step and make them as a left and right subtree of a new tree. Record the sum of their weight in the root. Repeat the step until we will get a single subtree. This single subtree is nothing but the Huffman tree. And how we are going to implement Huffman code in the sense, the left leg, that is the left subtree, everything we have to mark it as 0. Whatever the left subtree or left node that is there, that we have to mark it as 0. That is 0, this is 0, this is right one, and this is left 0, this is left 0, right? So every left subtree in all levels, we have to mark it as 0. And the right subtree in all levels, we have to mark it as 1. So here this right subtree is 1, this is right subtree 1, this is right subtree 1, this is right subtree 1. Okay, so here how we will create the Huffman code in the sense, in the Huffman tree, all the left subtree or left nodes, we have to mark it as 0, and the right nodes we have to mark it as 1. Okay, now the resulting code words are, for the letter A, you have to consider from root to its leaf level, where the symbol presents from root to its leaf level. If you are considering the Huffman code in the sense, that is nothing but code word for A. So code word for A is 1, 1. Okay, and the code word for B is from root to its leaf level of that symbol, we need to consider, that is 1, 0, 0. So code word for B is 100, and the code word for C is 00, and the code word for D is 01, and code word for underscore is 101. So these are all the resulting code words for the given symbol. So these code words we have identified by implementing the Huffman algorithm. And the tree constructed, the final tree, that is the single tree we got by implementing Huffman algorithm, that is called the Huffman tree. And the codes implemented for the left and right subtree is nothing but every left subtree in the Huffman tree we have to mention it like 0, and the right subtree we have to mention it like 1. Okay, and from the root to the leaf level of the particular symbol, if you are considering the codes in the sense, that is nothing but the Huffman code. So here, how we will encode and decode using Huffman codes in the sense, for example, if I wanted to encode dad, in the sense for D the code word is 0 1. Okay, and for A code word is 1 1. Again for D code word is 0 1. So if I want to encode the text dad in the sense, I have to implement 0 1 1 1 0 1. And if I want to decode 1 double 0 double 1 0 double 1 0 1 triple 1 0 1. So this is encoding. And if I want to decode this bit strings to text in the sense, here I have to consider like 100 in the sense I have to use this B, double 1 in the sense it is A, and then 01 it is D, and then it is 101 is there. Okay, so it is for underscore, and then so here you have to consider only double one. Okay, so it is for A, double one is for A, and 01 for D. So the decoded text is bad underscore AD. This is the decoded text. In this way only you have to implement encoding and decoding. For each letter of the text, what is the code word that you have to place it? While decoding, what is the bit symbol? For that, you have to place the text. So in this way only, you have to implement encoding and decoding using Huffman codes. So this is nothing but Huffman tree and Huffman code. We have discussed with one example. In the next session, we will discuss one more example to implement Huffman tree and Huffman codes.
Hi, in this video we are going to see about Huffman tree. Huffman coding is a lossless data compression algorithm. It reduces the size of data by assigning shorter codes to frequent symbols. This technique was developed by David A. Huffman in 1952 while he was a PhD student at MIT. Huffman coding is widely used in file compression formats such as zip, JPEG, and MP3. It ensures that frequently occurring symbols are encoded with shorter bit sequences, leading to smaller file sizes. It is efficient because it generates the minimum average length encoding. The main goal is to achieve optimal compression without losing any data. The algorithm creates a binary tree, known as the Huffman tree, to represent symbols and their corresponding codes. The coding is based purely on the frequency of each symbol. In this document, we'll walk through how the algorithm works and its applications. What is Huffman coding? A lossless data compression algorithm used to minimize the average code length for a set of characters based on their frequencies, named after David A. Huffman, who introduced it in 1952. Purpose of Huffman coding: to encode data in such a way that frequently occurring symbols are represented with shorter codes, reducing the total file size. Applications: used in file formats like zip, JPEG, MP3, and more. Understanding the basics of Huffman coding. Symbols and frequencies. Each character or symbol is assigned a frequency. Example: for a text document, symbols might include letters, punctuation, or spaces, each with a frequency of occurrence. Prefix-free property. The binary code used for each symbol must not be a prefix of any other code to ensure that the code can be uniquely decoded. How Huffman coding works. Step-by-step process. List all characters and their frequencies. Create a priority queue min heap and insert all characters with their frequencies. Repeatedly extract two nodes with the smallest frequencies. Create a new internal node with their sum A as the frequency, and reinsert this node back into the queue. Repeat until only one node is remain. The remaining node represents the root of the Huffman tree. Constructing the Huffman tree. Detailed tree representation. Illustrate the binary tree generated from the frequencies in the previous example. Assign 0 and 1 to branches of the tree, where the left branch represents 0 and the right branch represents 1. Generating Huffman codes. Leaf node representation. The codes for each symbol are determined by the path from the root to each leaf. For example, A might be 011, B might be 10, etc. Optimality of Huffman codes. The binary representation produced by Huffman coding is optimal, meaning it has the smallest possible average length for encoding the given symbols. Complexity and efficiency. Time complexity. Building the Huffman tree involves operations on a priority queue, which has a time complexity of O n log n, where n is the number of symbols. Space complexity. The space complexity is O n as we only store the nodes of the tree. Efficiency. Huffman coding is efficient in terms of both time and space for most practical uses. Decoding process. Decoding the Huffman tree. To decode a Huffman encoded message, you traverse the tree starting from the root and following the path dictated by the sequence of bits 0 for left, 1 for right. Example decoding. Given a series of bits, show how to decode them back into the original symbols using the tree built in the previous example. Limitations of Huffman coding. Fixed length encoding. Huffman coding is optimal for static frequency distributions, but it's less effective if the symbol frequencies change dynamically. Key concepts. Lossless compression. Lossless compression ensures that the original data can be perfectly reconstructed from the compressed data. Huffman coding achieves this by using codes while preserving the unique identity of each character. Prefix codes. Huffman coding generates prefix codes, meaning no code is a prefix of another. This property guarantees the unique decodability of the compressed data without requiring delimiters between codes. Frequency analysis. The algorithm relies on the frequency of occurrence of characters in the input data. Characters with higher frequencies are assigned shorter codes, while those with lower frequencies receive longer codes. Steps in Huffman's algorithm. The algorithm follows these steps. 1. Frequency count. Count the frequency of each character in the input data. 2. Priority queue min heap. Build a priority queue min heap where each node represents a character and its frequency. Nodes are ordered by frequency, with the smallest frequency at the top. 3. Build the Huffman tree. While there is more than one node in the queue, repeat the following. Remove the two nodes with the smallest frequencies. Create a new node with a frequency equal to the sum of the two removed nodes. Make the two nodes children of the new node. Insert the new node back into the priority queue. The remaining node in the queue is the root of the Huffman tree. 4. Assign codes. Traverse the Huffman tree from the root to each leaf, assigning a binary code 0 for left and 1 for right. Each leaf node represents a character, and the path from the root to a leaf determines its code. Encode and decode. Encoding. Replace each character in the input data with its corresponding binary code. Decoding. Use the Huffman tree to decode the binary representation back into the original data. Here is an example problem. The given values I equals 5, B equals 9, C equals 12, D equals 13, A equals 16, F equals 45. First we need to add the least vertices here. A and B are the least vertices. After adding the two vertices, the vertices is placed on the ascending order. Then the next step is to add the other minimum vertices. After finding the answer, we need to arrange the values in tree structure. Key concepts. Lossless compression. Lossless compression ensures that the original data can be perfectly reconstructed from the compressed data. Huffman coding achieves this by using variable length codes while preserving the unique identity of each character. Prefix codes. Huffman coding generates prefix codes, meaning no code is a prefix of another. This property guarantees the unique decodability of the compressed data without requiring delimiters between codes. Frequency analysis. The algorithm relies on the frequency of occurrence of characters in the input data. Characters with higher frequencies are assigned shorter codes, while those with lower frequencies receive longer codes. Advantages and disadvantages. Advantages. Optimality. Huffman coding provides the most efficient coding for a given set of character frequencies. Lossless compression ensures no data loss during compression and decompression. Wide applicability, suitable for various data formats and applications. Disadvantages. Dependency on input data. Compression efficiency depends on the frequency distribution of characters. Overhead. Requires storage of the Huffman tree or frequency table for decoding. Inefficiency for small data sets, not ideal for small input sizes due to tree building overhead. Extensions and variants. Adaptive Huffman coding updates the tree dynamically as data is processed, eliminating the need for a frequency table. Canonical Huffman coding simplifies decoding by arranging codes in lexicographic order. Arithmetic coding generalizes Huffman coding by encoding entire messages rather than individual characters. Conclusion. Huffman's tree algorithm is a cornerstone of data compression techniques, offering an efficient method for reducing the size of data while preserving its integrity. By constructing a binary tree based on the frequency of symbols, it assigns shorter codes to more frequent symbols and longer codes to less frequent ones, achieving optimal compression in scenarios where symbol probabilities are known and static. The algorithm's applications are vast, ranging from file compression formats like zip and gzip to multimedia codecs such as MP3 and JPEG. Its effectiveness lies in its simplicity, elegance, and guaranteed optimality for prefix free encoding. Despite its advantages, Huffman's algorithm has limitations, such as inefficiency in adaptive scenarios or when probabilities are unknown, where alternatives like arithmetic coding may be more suitable. Nevertheless, Huffman coding remains a foundational technique in computer science, exemplifying how mathematical principles can solve practical problems in computing efficiently. In conclusion, Huffman's tree algorithm demonstrates the power of algorithmic thinking in solving real world challenges, continuing to be a fundamental concept in data compression and beyond.